Good morning, everyone. I will try to keep the materials interesting and then keep you be here until 12 and for the more important session. Okay, I'm Hongjing Liu. I'm a faculty member and in psychology department. I also have a courtesy appointment in statistics department. So I'm going to give like 2 tutorials and then really to talk about how we use computational models in psychology and to study the human cognition. So today's first talk is so wonderful. I learned so much. But this time, we will get into a kind of a different aspect to look at intelligence. So as a psychologist, I think, oops, how did I make this move? Okay. As a psychologist, we find it's very interesting that intelligence can be manifested in many different systems. And then, especially, and then it's exciting, and then this basically in this program will bring and then people from all these different aspects of the different intelligence systems. So one way for us to look at the different systems like machine intelligence, animal intelligence, human intelligence, for us, one way is to use these computational models and to compare the different systems to see the differences. But meanwhile, we also want to find the commonalities and the common mechanisms and shared across the different systems. So to study this problem, we take the cognitive science approach, and then so cognitive science is famous for having this hexagon, and then to show, and we study the intelligence and the human mind, and from this multidisciplinary approach. So you can see that all these different fields, and they interact with each other, and then try to find the balance and between this, I call it analytic approach. We're trying to understand the existing intelligent systems, for example, our brain, or very complicated AI systems. And we also are interested in this synthetic approach and to help us to build new intelligent systems. So now if we look at these types of approach, and we borrow all these ideas from the different disciplines, and then we connect them together. So one of the lessons we learned in cognitive science, it's almost we can think about it's reverse engineering of the mind. One of the basic ideas is to look at the intelligent system so that we can give them this functional analysis. We can answer the question, how does it work and why? And then from the functional perspective, and then the explanation capacity, and then basically trying to answer these 3 different types of the questions. So first is what are the parts and what are the components of the mind? If we have all this intelligent behavior, so what are the fundamental components in the mind to support this intelligent behavior? We're interested in the respective roles, and then what does each of these components do, and then their organization. So if we look at the psychology, and then we decompose it, and then the mind into someone study perception, someone study memory, someone study decision making, and so on. For the brains, we also have the corresponding different functional regions and related to this different capacity. So one way to think about it is if we think about all our system, is how we have input and output. If I think about the most simplest, the information, basically processing system, is this morning you just use your coffee maker. And then you have the input, and then you have the water, and then you have your coffee, and then so eventually the output will be a cup of coffee. If we look at this system, we are using this system, so we can get this output and a cup of hot coffee and from the input here. But now when we look at this coffee machine, we notice that they have the different components. And each of these components, and then they have their functions. So sometimes, and then we have the component switch and the valve, they have totally different function. And the switch is just trying to start or to end and the process, but the valve have different ways and a different function and make sure and the water and the flow in one way. But sometimes we also have the same component, and then they work for 2 different functions. For example, this coil. And then this coil can help us to boil the water. But meanwhile, this coil also have the secondary function to help us to keep the coffee warm. So this kind of functional analysis aspect, one thing is really just like taught us in the past, is we can decompose a complex and intelligent capacity and into a network of less complex capacity here. So, but on the other hand, decomposing and then the complex capacity and into a less complex capacities does not tell us and the software how you do the computation and in this case. And we can decompose them and into a different brain regions, but the question is that how the mind and can do the computation so that you can observe and these intelligent behaviors. So here I want to show a few of my favorite examples, and just to convince you, your mind is always computing something. So for example, this is my favorite color example. So now I show you, and then these two, and then patches here, and then in the first and the surface here, if I ask you, and then this region, and this A1 region, and A2 region, do you perceive them, they have the same color or different color? And so the same question, and the B1 and the B2, and in this surface, do they have the same color or different color? So I think everyone, I don't need to do like an online experiment, because right now everyone perceive A1 and A2, they seem to have the different colors. A1 patch is darker than A2 patch. But now, if I just change the surface geometry and using 3D and these types of software, now B1 and B2, they seem to like have the similar color here. So actually, I'm not cheating. It's actually, I can want to tell you, all these four patches, they have exactly the same color. Now, if I just like cover all the local context, and what you see here is that they have exactly the same color here. But your percept is very different. So this actually is a miracle for us, and that's kind of like very amazing things you can get from visual illusion. And that shows that your brain has this computation, you apply this standard computation to these so-called tricks and made by psychologists, and then you can find a very dramatically different experience. So in this case, and then all these four patches, they have objectively, they have the same intensity, but your perception is very different. Why? And then part of the reason is that you can contribute to that, your mind continually to do this computation. But what computation the mind is doing? So here, the idea here is that your mind is always trying to interpret the input, and then their computation is trying to elaborate and manipulate them, and then to obtain the output here. So now, when you're doing this elaboration and manipulation, this can be done through the computation. But why the mind need to do this computation? You probably can ask this question here. The interesting thing is that what you want to perceive is the color of the object. So I can show you a slightly different illustration here. If I show you this basket of the fruits, and now you can see that it seems like it's behind this transparent and blue shade. If I ask you, what's the color of this fruit? And then many of you still will perceive it's orange, right? Now, if you look at the situation here, is that now, this one is what your perception is more similar to the left and then to the right. But if I cover under the local context information, if you only based upon this patch, you should tell me it's a purple, and this orange color is purple, but you did not do that. And then why the mind need to compute? If like for this very simple illustration, you can see that what you get is not what you need. So you have to do an inference and to do this computation. So for example, what you get is the light and then the photons entering your eyes, you get the luminance. But the luminance in the image, or what you get by your brain, is actually it's a product of the two entities here. The first one is the color of this object, and then you can think about its reflectance, and then what this fruit and the color should be. That's what you need. You want to see what's the color of this fruit. But it's influenced by the lighting from the environment. So that's the illumination.
Wait, but in this case, wasn't it just memory? We see orange because we remember that.
That's the good point. Yes,
not really
and then you could
at all. It's memory. It's memory.
Yes, memory is one important factor. So later I will talk about it. But like when we look at the illusion, I showed earlier this different patch and so on, and then that's actually not memory. That's the first like new object you have seen. So what happens is that even though we have the memory, we have the knowledge, and then the computation we form, then in the natural environment, we actually can transfer it to this artificial stimulus. And then we can reveal these types of visual illusions.
But I bet you that if the blue background was not a big square that suggests to us there's a filter of some kind which was concentrated on the orange, we would not have perceived it as orange, right? We would have probably perceived it as some kind of purple-like thing, right? So
that's a very good point. And then so what we perceive tend to be like between this purple and the perfect orange there. And we do take into consideration about this local context and our knowledge about the local context. I will talk about that in the next slide.
Maybe to contextualize a bit, what does computation mean to you? Because I'm not sure how, is this an answerable question? Does the mind compute?
Yeah.
What is computing?
Yeah, so actually I will have the example here right now. So this actually to me is a computational problem because what you get is the product of these two entities here, right? So if you think about, if I have a number and then very simple, I just like really simplify the computation, what you get is a number 60. But the 60 is the product of these two entities, A and B. And then what you really want to get is the A. What's the A's value? And now you can see that it depends upon the B's value. You don't need to estimate the illumination, but what you really want is like what's the color of this object. Now you have to figure out how I'm going to decompose and then this 60 and then to the product of the two values and then which of the value is the color of this object. So then this kind of like the whole thing, I will consider them as a computation here. So now in this case, and then one thing I want to convey here is that it's not easy. Even though if you perceive the color of this fruit, it's very easy. But the underlying computation is not easy because you have this uncertainty in this computation. However, you have knowledge. That's kind of earlier we talked about it. We have the knowledge. Generally, we know what the fruit of the orange would be. So that will help you to add one type of constraints. And you also have the knowledge about what the illumination could be in the indoor environment, in the daytime, or at night, or in the outdoor environment, and so on. You have the general knowledge here. You can add a constraint here. You also have some other kind of like more detailed constraints. For example, you know, the illumination or the lighting does not change too much. And then because the lighting will get into the entire room, and so their change is very gradually in the local region. But the object's color can change dramatically from one fruit to another fruit. And all these kind of constraints in the local context, in the global context, can be added into this computational problem, then help you to solve this problem.
Yeah. I have a clarifying question. How do you have certainty that the computation is done through multiplication and not another operation?
Yes, that's a very good question here. So now in this case, I will just simplify the situation here. So later, I have another even simpler example to show you. We have the ways to justify for some of the tasks, and then we have ways to justify. You have to use this operation. But for the other things, we don't know. And then so it could be another nonlinear function, and then here, more complicated function. So you can see that why it's easy for you to perceive the color of the object, but the computation is not easy because you have a lot of unknown variables. You also have the function how to connect these variables and to lead to the luminance, and then that also will be the need to be determined factor there.
And just to follow up to the earlier question about the, I guess, definition of computation you're working with, here, are you just meaning that like we can observe some equations about human behavior, and so we're going to take that as a working definition of computation? Because I guess, you know, we can observe equations in the weather, but we don't usually think of the weather as computing.
Right. So now I think it's related to that. So so here the computation is more like we have some kind of observations, but this observation does not like directly answer what we're interested in. So there is a lot of like latent variables and the latent functions can influence and this mapping from your input and to your output here. So in this case, that's what I will consider that as a computation. Okay. So now in today's lecture, what I'm going to introduce, I think the most profound equation, and that you learned is in stats 101, and then so what you learned is the conditional probability, and then basically is that you have two variables, and then now you just switch them around. My undergraduate students say, then you get the base rule, right? So, but the interesting thing happened here is that beyond the probability theory is that you gave some meaning to each of these variables. And then what you can see is that this actually tell you how you're going to update your knowledge. So you can see H here and indicates the hypothesis. That's something you want to know. What's the color of this fruit? D is the data. What's the intensity and in the image? Or what's the colors and the light gets into your eyes and so on. So what you have here is that you can think about now, I suddenly have a way to decompose things. So for example, and a hypothesis I'm interested in is that what's the color of this fruit? If I know this fruit is orange, I have some prior knowledge about the color of this fruit before seeing this image. So that will be this kind of constraints could be incorporated into the prior. And then now I also have some kind of knowledge to say if this is the orange, and what's the orange could look like. So that will be incorporated into this likelihood function. So this in both of these components, and they capture the different types of knowledge, but they both can influence and then you inference here. So this kind of function, this very simple, so-called simple equation, but it tells you is that now you have some previous knowledge here. After I observe the data, I'm going to update my belief. And then you can decompose this into these two components, likelihood and prior, and you can study it. So now what I'm going to, I will quickly just remind that everyone here and the terms and we're going to use and we learned from stats 101 is that we have the prior probability distribution, we have a likelihood and to capture and your knowledge, how the data can be generated, and then we combine them together, we update our belief. So now in this case, even though it's a very simple equation, to combine these components together, in a sense, I think, capture the essence of functionalism, and then to tell us that we can decompose the computation into these two components. But it did not tell us how to get the distribution here. Question?
Yeah, I guess my question goes a little bit into that. So I was just wondering if your approach to cognition is Bayesian, then what would you say is a mechanism or a computation that can explain how the hypothesis come to be? Is Bayesian updating is a way of updating your hypothesis, and what is a Bayesian mechanism that allows you to construct hypothesis in the first place? Yes,
that's a very good question. And then that's actually something I'm going to touch on and then in the second tutorial. It's in the first tutorial, what I'm going to assume that here is that this hypothesis space is already defined here. I know these are the set of the hypotheses, and then we can use this computation and to do that. But then the question comes to where this hypothesis space come from, and I think that's $1 million and the question here. And then so I think this part, but on the other hand, then using this kind of mathematical framework, one good thing for psychologists is that will force us and then to make the constraint explicit. Whatever the assumption you are using about the hypothesis space and about the probability distributions for prior and then about the generating functions for likelihood, you have assumptions there. Then that's actually open the door and for experiments and to test these assumptions and so on. So that's kind of the one benefit we get and from these kind of mathematical models. Yeah.
Just to relate this to it, I remember from Stats 101, that big sum on the bottom, that's just P of D. Right? Yeah.
Yes, just a P of D, exactly.
And the more basic Bayes law is just with the P of D.
Yeah, yeah. So that's kind of if for psychologists, it's if we can design an experiment, get rid of this denominator. That's great, because that's most of the computation we'll get in, right? So that's kind of why we love the two alternative forced choice. because we get rid of the denominator and in the inference and so on. But that's the side story here. Okay, so I think here what it's showing is that we have these types of like mathematical framework and we can borrow and then to separate it into the different components. But now the question is that why does the mind compute? Okay, so now earlier I already like pointed to it, is that we can decompose them into different components, but we don't know under the representations what's the computation, what's compute and for each of these components. So what computes here? So one thing I really like under the, oops, I think I moved too fast. I really like and then the quote from Richard Scheffering was talking about why does the mind compute? And one way to think about it, and the mind, it really kind of consists of like this set of the models, and these models are supported by the brain. And then this model, and then it basically you can think about it, it's just trying to make the best guess about the entire environment, and including yourself and your body, and then the physical environment, other agents, and the social environment here. So in other words, under the mind, and then you can think about it's a set of the models, and which can help us and to infer under the likely state of the environment, so that later, and then you can learn, and then to make the inference, and you can make predictions, and then you can produce actions and behaviors here. So that makes this kind of mathematical modeling, I think, is very appealing for cognitive psychologists.
I know it's a quote, but I would like to push back a little bit that probably the model is more like a distribution over the states of the environment rather than the best guess of a single state of the environment.
Yes, exactly. Yeah, I totally agree with that. And then when you measure the behavior, also it's it's an interesting thing, right? You can make the behavior measure is more like the best estimate of this model, or it could be a distribution. If you pull on the individuals and then behaviors together, you could get a distribution and so on. Yeah.
Maybe just to push a little bit more back.
Yeah.
There's also a certain amount of us being stuck on a particular choice. Meaning to say that if you show me an illusion, for instance, and then you tell me, well, it's like that, we will actually be stuck on that choice for a while, and then we will revert back to some other state, which this does not model at all, right?
I think this is kind of more general, because the idea here is the model still keep to learn, and then to modify the models and so on. If you think it's like not a model, and then but the model still can be dynamically updated, and depend upon your learning data and so on.
But our ability to take new data into account depends on our fixation on a specific model. So if we think it's an orange, we'll actually take a lot more data to convince us that it's not than if you somehow, before we made that decision.
Yes.
So this is not reflected in that at all somehow. It's once a computation is made, we stick to it somehow, as opposed to just evaluating it without any.
That's a very good point. As I think in the other case, if you start to consider the model kind of in a hierarchical ways, so people like at some point, and then they could switch to the different types of the model, and then so that's actually very interesting things that later will lead to connection with the social sciences, where this belief polarization can come back, and where this kind of like black, kind of like the other types of belief update, and it really can change in the people's mind and so on. So I think people still. Personally, I feel like human intelligence really lies on this kind of adaptive nature, and they're willing and then to make the switch, and then if there's other kind of data and information coming. Yeah.
There's a number of examples in which the way people make prediction or come to conclusions is quite in tension with Bayesian approach. A classical one is in which there's a disease with a very low prevalence in the population, and there's a test which is not perfect, and then someone tests positive, and everybody tends to say, oh, that person is likely to have the disease, but when you do the computation, it turns out that the probability is very, very low because the prevalence is low, and we don't take this into account when we process this information. So how do you react to this fact that there are many instances, well-known instances, in which our intuition is at odds with Bayesian rule?
Yeah, actually, we can hold on this like my answer to this question. I have an example, and then kind of to show, and in some situations, and at least in that one example, it's showing, and it seems like we're making decisions. It's very different and from rational models and then prediction and so on. But we actually can trace back and to see what are humans' priors could lead to and then these types of the decisions. So I think in some situations, and these types of behavior could arise from human actually use and the prior knowledge is different and from the external environment. And then so kind of especially in the learning or teaching scenarios or young children's scenarios, if you think about their knowledge and it is limited, and then they could have these kind of biases and then kind of knowledge and then insufficiency and then from their learning environment. Sometimes it's come from and then the likelihood term. And then we could make the wrong assumption about how the data could be generated. What will be the underlying causal models to generate the data? When we make these types of wrong assumptions, that also could lead to types of the behavior like this. Yeah.
So when I perceive something, it's usually not probabilistic. Like in the illusions you gave, I think one shader is darker than another shade, but I don't feel like it's a probabilistic perception.
Yeah.
So how do you go from Bayesian probabilities to how I perceive, which is not probabilistic, but
yeah, that's a very good question. In some cases, and when we just whenever you have this uncertainty and in your input data, you could use this probabilistic model and then to approximate it. And then so I think even though the data you could give to people is just a contingency table and so on, but we could assume, and for example, the cause and could be probabilistic. So intermediate mechanism could be a random variable and then follow certain distributions and that lead to this kind of contingency table. So that's what we usually kind of introduce this type of probabilistic model. So even though your observation looks like a deterministic, but your underlying and then the mechanisms and will be relevant to the probabilistic variables and so on. Mm-hmm.
Yeah, maybe this is related to the last two, and potentially you're going to answer it in the next bit. But I guess what's the evidence then that the mind is running? If it doesn't seem to like us, like we're doing Bayesian inference, and there isn't, what's the evidence that our brains, at the hardware level in some sense, below our perception, are actually doing this Bayesian kind of approximate inference kind of?
Right. That's you basically we can jump into my conclusion slide. It's not we do Bayesian all the time. I'm just giving you a few examples, like we have the good start, and then but later you will quickly find in a lot of situations we're not Bayesian, and then we have our own assumptions and so on. So, but here and today I'm going to show the two examples, kind of to show, and then we could use this kind of Bayesian types of the models, and then as the tool and to study kind of what kind of assumptions constraints people could use.
What is the word "it" towards the end? It uses. I mean, it's a separate agent that's.
Yeah, I think it refers to the mind.
The mind itself.
The mind.
Is the
yes.
model.
Yeah. Yeah. Okay. I will use, so first before and then I get into these two examples, and then I want to just quickly and then review and one of like very kind of popular and views and in cognitive sciences to how to study the computing system. So this actually is a very, this is the example, and then it's a machine and from the Tinker Toys. So for example, let's say, and then we actually open this machine up, and then we look at the entire structure. And then every structure and we look at, and then we actually build another machine exactly like this. So then, but the question is that if we build up this replica of this machine, do we really understand what this machine is about? Do we really understand and then what kind of like computations and this machine is doing? My answer is kind of like no. What I'm trying to do is like now I'm just replicate and all these mechanics, but we don't know and what this machine is doing. But if I tell you what this machine doing, it's just to play on the tic-tac-toe and the game, you feel like you really know it, right? You feel like you have a better feeling about you understand the function. After you understand the function, and then it seems like all these types of structures make sense here. So that's kind of like an approach, and this actually will lead to the basic ideas, and then raised by David Marr, and back to the 1980s. It's like, at what level should we try to model human cognition? So he actually raised this question, and then in his book called, even though it's called Vision, but the first chapter, it's very fundamental, and it raised a good question is that when we are trying to analyze the computing system, we need to know what's the goal of the analysis. So now I'm going to use a very, very simple information processing system, kind of to go back to an earlier question. In some very simple systems, we can exactly justify why we use these operations. So this is like the earliest the cash register system. Right, so we're going to analyze this simple list and the information processing system at the different levels. So the first level, we call the computational level. So it's just trying to answer the question, what is being computed and why is being computed? So for this particular system, it's very simple. So what are the inputs? And for this cash register, it's a bunch of numbers. And then you buy several items. Each item, they have the price. And the output, you want to have one number. You only want to pay the total cost. So the goal of this system is just to compute the total cost of the set of items, and then giving the price to each of these items. So clearly, everyone knows we do addition. We don't do multiplication, in this case. But now the question is that why we do addition, not multiplication? If we look at the additions and the properties, we know all this like addition, commutative, associative, inverse, and the zero elements, and so on. Then we realize that each of these properties, and then for this formal operation, exactly can satisfy the functional constraint for this information processing. If you think about it, you buy nothing, cost nothing, that corresponds to this zero element, constraints, order of putting the prices, then the matter. So that's commutative and the constraint. And the grouping doesn't matter, that's associative property, and in addition. And now, seems like all these things, finally, if you purchase something, you return something, that should be zero. So you get the inverse property. If you look at the multiplication, they can satisfy some of the constraints, but not all of it. So that turns out addition is the only formal system that can satisfy these functional constraints.
What about addition mod 3?
Sorry?
What about addition mod 3?
Addition multiplies.
Mod 3, modulo 3. It will satisfy all these same constraints.
Oh, yeah. That's actually a good point. So addition modulo 3, right? So then you could consider then whether there's other types of the functional constraints then you want to add if you want to increase the complexity of the system and so on. So it's not. Yeah, so it's not like always you end up like with one formal system. And then the other things also depend upon the purpose of the computation and what you want to try to do and why you want to do. So this is just like a very simple example to say, at least compare addition versus multiplication. Addition, and then it's like the only one can satisfy these constraints.
I mean, it has finite size, so it is actually mod something, right? And the register
It
can't
is
get
mod,
bigger.
mod,
It is some
100,
mod.
yeah, 1,000 cents or whatever, but yeah.
Yeah.
Just add an axiom here, right? That grouping divergences are like monotonically non-decreasing.
There's a notion of value that decreases as you buy.
Sure, yeah.
There's an order. Up to $100.
Okay, so now this is like the one of the reasons we think about why, if we build, we're trying to understand the intelligent system, these functional constraints are important for us because the functional constraints will help us to identify what kind of like computations we want to do. Now the second level we want to do is that to analyze what are the representations and what are the algorithms for this system. So many formal systems, so we want to represent the numbers. We want to represent this addition operation. And then we can have a lot of choices for representations. So in this very simple case, you can think about it. And then this representation, you can represent the numbers using the real numbers, and the prices using these real numbers, or you can represent the prices and using the binary numbers. And then you also have this mapping and between the representations of the input and to the representations of output. So this also will become an important and the issues and related to the representation. And also it turns out that you could have different types of the representations. You could have the representations and based upon the real numbers. You could have the representations and based upon the binary numbers. Now, if you want to, you notice that for some tasks, and the one representation format could be better, or could be more efficient, or easier, and then the other and the representation format. So for example, if you think about, I want to find the powers of 10, and the real number representation is better. It's easier to compute. But if you want to find the powers of 2, binary, maybe it's a better choice. So now the third level, and it will be related to implementation. So what will be the physical implementation of this system? You can think about it here, and then for this adding and all these prices together, and for the cash register system, you could then implement it through the modern chips and the computers, but you also can do this computation through the abacus and so on. So this actually leads to the Mars and the 3 levels of analysis and for the intelligent system. And then we want to at the computational level, and we want to answer the question is that what's the goal of the computation, and then why it's a proper and a computation, and what's our logic and the strategy, and then we can carry and for this computation. And in the representation and the algorithm level, and then that's more focused on how to represent the input and output, and how to represent the algorithm and form the algorithm for the transformation from the input and to the output. So implementation level is that how we implement it, and then all these kind of representations algorithm for solving these computational problems can be implemented using the biological system in our brain, or can be used and then just like to implement and in the AI systems and so on. So one thing I want to emphasize is that actually these 3 levels, it's not like they're independent from each other. They actually can constrain and then each other, and then depend upon and then what representations you are using, and then that could lead to what kind of a computational problem could be easy to solve, and what kind of a computational problem actually will be hard to solve. But the implementation also can constrain what the representation algorithm could be. And then some like representations could be very suitable for the biological system, but it may be very different from artificial intelligence system. Also, when we talk about the mathematical models, and then mathematical models in psychology, and also could be built and then at all these 3 different levels. And then at the computational level, and then you can just mainly to figure out what will be the optimal solution. And for these types of tasks, you can compare and with the human performance and to try to find out if human have the suboptimal performance, and then where and this suboptimality come from. And then you can also like build up and then the models and based upon the cognitive processes and how you represent and then the information, how you encode the information, and then later and then in the algorithm level and then how you retrieve this information. And then you can also build up the models and then based upon how neuron and compute and communicate and so on. So I just gave you a quick example. So for example, this is the memory model. And then this memory model and then developed by the researcher is like to try to explain on the human memory system and then based upon our neuroscience knowledge about hippocampus neurons. So that you can just like build up on this system to mimic and then the different types of neurons in hippocampus, and then you can test the capacity of the memory system made from these neurons. You can also build up the model and based upon the assumption about the representation and the algorithm. So you can assume like now I'm trying to remember all these items. Now I can use this specific encoding mechanism to encode the knowledge about each of these items. And then we can form this item and based upon the matching features to determine how likely I will succeed in retrieving this information and so on. So finally, and then the same memory kind of a system, you can also build up the computational system, computational models to explain and then why we actually forget things. And is that a side effect of the human memory system? Or you actually can explain to figure it out that's not the side effect. And the forgetting and then actually showed what human systems are being like actively and then to adapt to this environment. So why are we adaptively to do that? Because we want to encode and then also trying to retrieve the most valuable, most important information and in the memory system. And so this forgetting and the behavior and from human memory system, it's not like really the bad thing. It's actually the optimal solution. And for us and to show and the human system is trying to encode and the environment and with the different and importance and so on. So this is just like a general example and to show and we can build up and then the mathematical models at the different levels and trying to explain and then human behavior. And then so depends upon the different levels and then we actually can address the different types of the questions and so on. So today I'm going to just show two examples here and then very simple example and basically, we can try to analyze these examples from the computational perspective and to see what kind of circumstances and then human actually gave and then the like rational decisions in what circumstances they don't. And then another thing I also want to show, and then to answer these questions, we do need to have the synergy and between the mathematical modeling and the experiments here. So this is a reminder here, and then in these two simple examples, and we just have the different data, different types of data, different types of hypotheses. So the first example, and from the Griffith and Tannenbaum's paper, and then to talk about everyday prediction problem. This is a very simple problem. If I tell you, you meet someone who's 78 years old, what's the lifespan of this person? How long and will they live? You have some kind of a general kind of like guess here, right? So not only and then these types of prediction problem, if you from the computational perspective, you actually can extend it to many different domains, not only the lifespan. And then, for example, you can extend it to estimate and the profit from a movie. I will tell you the currently and the movie and then has made and the 60 million and to date. And then you're trying to estimate and what's the total profit and from this movie. And then, or you can do them. Okay, you have been baking and then something and then for the oven, in the oven and for 34 minutes. How long can you finish the baking? And then you can see and then these are all these kind of different types of domains, but your computation and share something similar, which is and then you are encountering phenomena or event, and then so now in this case at the random time of the value t. And then your job and your computational inference is trying to estimate the total extent or the duration. You meet someone and who's like 35 years old, what's the total lifespan and in your prediction? So this actually has an early paper. It's interesting, and then they did the experiment. If you say, okay, if you meet someone who's 35 years old, and typically people tend to estimate and 70 years old and then being the lifespan is reasonable. So this is called the Gold's rule. So at that time, and then it's presented as a human heuristics, right? So somehow we have this like a double rule preference, and we just double it. But you can see that I gave you the early example. You meet someone who's 75, that does not make any sense. You apply this rule. And then, so what's going on here? So if we use and then adopt this Bayesian framework, and then we can just look into this prediction problem. So now, in this case, even though data we gave to you, it's almost deterministic, which is 35, and then just one number. But if you can decompose this problem and into and then the likelihood and the prior here. So likelihood basically will just like capture and then you knowledge, you understanding about this data. If you say we just like capture the knowledge is that if this person is 75, like lifespan is 75, you have equal probability to meet this person and during his lifespan. And then so that's capture and this random sample idea for likelihood. Now the prior is interesting and focus and for this study. So we do have some kind of prior knowledge about how old and the people, what's the lifespan of the person. And we also have some general knowledge on how long we need to bake the cake, even though we have the individual differences, but you have the rough kind of general knowledge. You also have like general knowledge of how long and then how many lines the poems could have and so on. So now you can see that we can put in some kind of distributions to look at whether it's matched to human performance. So one of the ideas is that, and then you can impose this random sample assumption into the likelihood term. You can use this uninformative prior and to put into as a prior distribution. Now, if you do this, if you adopt and then this likelihood function and then adopt and this prior distribution, and then you do a little bit of mathematical derivation, and then what you notice that you can, for a particular and a prediction problem, you can exactly plot what the posterior distribution would be for the lifespan. So now if we take this distribution and if we take the medium here, we exactly end up with the Gauss rule, and then basically we'll say you just double it. So this doubling and actually come from your assumption about what will be the prior and then what will be the likelihood. So now you can see that, and then so in this case, earlier I already raised this issue and why this double did not make a lot of sense, and then in some of the situations. So now in this case, what you can do is that now we can keep under the same likelihood because the random sample is a pretty reasonable assumption and in this prediction problem. But we can look at the prior distribution. How we can look at the prior distribution? We actually can look at when you introduce different types of the prior distribution, you should expect that human judgment will change. So this is just purely on the simulation work and from the mathematical models. When you introduce the different prior distribution, you can use the power law prior, or you can use the Gaussian prior, you can use the Erlang prior, different distributions. Now, if you plot and then you estimated, for example, lifespan with your observed age, and then you can see that they have the different relationship and between your predicted lifespan with your current observation number. So that showed the interesting thing for experimental psychologists is that then we can design an experiment and to exactly measure humans' behavior and for this relationship between the predicted answer and with the observed data, and then try to figure out what kind of priors people could use. So now in order to do that, and then one extension is that you don't measure and then in this case, and the other things that we also can do is that to figure out what are the priors here. If you look at the different domains, and then we actually could go to the natural statistics to measure and then what's the lifespan of a person, and then how much and the movie could profit, and then you could find and then what's the total number of lines, and for a poem, then we do notice that and from these natural statistics, and then they will follow very different distribution here. So now, so here it just indicates the histogram, and the red lines just indicate the fitted and the distribution, and using a specific form, and so on. So we can look into the natural statistics. If the human participants and they use and then this general prior knowledge distribution in their judgment, that should be reflected and in their behavior in this prediction task here. So from experimental perspective, an important thing I showed earlier is that to really look into the relationship, we do need multiple measures. So this actually also go beyond the Gold's original study, rather than you ask like one observation data and to estimate the lifespan, you ask them like 5 different values. You meet someone 60 years old, you meet someone 30 years old, you meet someone 70 years old, and so on. So then we can measure this relationship, this function here, and then try to capture with human behavior. So this actually is experimental data, and this for different domains, and the dots here and indicates the human aggregated judgment If you can run like 50 subjects, each subject gave you the prediction. When you meet someone, for example, you meet someone is 35, and the people will estimate their lifespan, and then these black dots and indicate human judgment, and for these 5 observed data point, and the lines here and come from the model prediction. And the black lines, and that means I'm going to use the prior, and just in a non-parametric way, I'm just using exactly the measured histogram. And the red lines and come from, you can just use a fitted distribution here. So across all the 5 examples, and including the cake here, and then so because the cake and the histogram is difficult to fit with the standard distribution, we just use the histogram here. So you can see, and then this model actually predicts the human performance very well. So what that show here is that we actually implicitly using the knowledge about from the prior distributions. And then the prior distributions we use for making this judgment is quite close and to the natural statistics and the domain knowledge here.
It's a great question. So the black is the red is the ground true, right?
Oh no, the red is just the using the prior distribution.
Right.
The fitted
Sorry, that's what I mean. That's
yeah.
from that. So could you go backwards, like to figure out what humans' prediction, like what their prior is on representative?
Yes, that's in the next slide. Yeah, yeah. So, but there's one very interesting example. It's this, and there's one question which say, and you learn that in ancient Egypt, and there was a great flood, and in the 11th year of the Pharaoh's reign, how long did he reign? And this is one example, and then you can see that this is the natural statistics. We can go back to history. We know and the reign duration, and then for each of the pharaoh. And now, what you look at, these are the human judgment. It's quite away and from, and then the prediction from the model if you use and the true history here. Now you actually can go back and then to look at, okay, from and then this human's judgment, we can go back to estimate and what's the prior distribution, and then, oops, that is showing as blue. And then that's the distributions and the human tend to use. So you can see this is the difference between your subjective knowledge about like the duration of the pharaoh's reign with the history, because we actually don't know. A lot of them actually have a very short period of the reign here. Yeah.
Is this consistent in the sense that if I change 11 to some other number and estimate the distribution, do I get the same estimated distribution for people?
Pardon?
Like if I ask a different question to people, if I take a different survey where I ask how long did the pharaoh reign?
Yeah.
11. I mean,
I would expect so. So you can ask. So you kind of like rather than go back to the history book, and we can ask people, okay, like based on your knowledge, and then what's like the duration and so on. I think that's, yeah. So I think that will end up something will be similar as this.
Have people done experiments or?
No, yeah, not for this particular study. Yeah, but in general, you can ask people with this knowledge. One of the difficulty parts for experimental design is that you can ask the people, but then everyone tend to give you the mean of the distribution. The question is how you can measure the distribution and systematically. That's the tricky issue experimentally. Yeah.
Do you think it's possible that people are instead picking a random year rather than a random pharaoh? Because a random year would have a pharaoh that lives longer than average. Reigns longer than average.
So random year, you mean like from this distribution?
Yeah. So if you have two pharaohs that have short reigns and one has a long reign, if you pick a random year, you're just as likely to when the long reign is in the short reigns. Whereas if you pick a random pharaoh, so is it possible that like their distribution of the pharaohs is what's different rather than their estimate of the lifespan of the pharaoh?
Ah, okay. So the question is like, rather than this kind of reign period, so kind of almost like this distribution, or this variable, and then they misunderstood it, and rather than the duration of the reign.
Well, I'm not even sure they're misunderstanding, because if you pick a random flood, that's more likely. If there are three pharaohs, one had a 20-year reign, two had 10-year reigns,
right,
and you pick a random flood, which occur randomly in the years,
yeah,
there's a 50% chance it occurs in a 20-year reign. So your estimate should be higher than the mean length of pharaoh's reign.
Right.
So is it possible that they're just correctly doing that?
Okay, that's a very good question. But I think in this case, because they measured at all this a range of like this 11, and there could be 11, could be 5, could be 3, and so on. And then if they consistently and using that strategy, I would expect that and they still have to capture and then relatively the information about this distribution, rather than just say, okay, I have a longer time, 50% and more than. And I think that could be making the distribution too qualitative. That would be my guess. And then so in this case, and part of the reason here is that I can give the data and differently. I could be 11, 5, and 3, and so on, but they use the same computation and to do the to do this inference and so on. Okay. Yeah, but that could be some kind of like a strategies and people will use. But the question is that whether it's just a kind of individual group of subjects could use this strategy. But what we hope is that by running large number of the subjects, and then you can wash out and this strategy difference, and more kind of a conversion to this kind of generic computation here. Yeah. Okay. So the other, I will give another second example in this case. And then so now the first simple example is more like you're answering the question for the prediction. You're trying to predict, and then this total quantity and so on. The second example is pretty much still, and we're using this Bayesian framework, but we apply it in a very different domain. So for example, and motion perception. And so in perception, I will show you here, mainly I will emphasize on, and in these types of data, even though we perceive the movement of the object and very well and then very easily, but actually there is uncertainty and in the data, so and then your system and need to deal with that. So there's one of this uncertainty, and then in this case, so let me just double check the time. Jacob, should I end up 12 or? Yeah. Okay, so 10 minutes. Okay, so now, and the first thing I will just use a simple illustration. So for example, I will show you 4 dots on the screen. They're going to move and from frame 1 to frame 2. And then so this, you can see and what's your perceived motion and from this group of dots. So these are 4 dots, frame 1, frame 2. So many of you perceive it's all these 4 dots and then they move and then to the right, and in this case. However, and there is an inherent and a correspondence problem. So in this kind of illustration I'm showing you here, the black dots and the indicates and the location in the first frame, and open circles indicate and the location, the dot location in the second frame. So this is what you perceive, right? So, but think about it, and when you show and then this display, every dot and they look identical. You could have something like this dot and it could move and then to this closest position, or could move into this far position because all these dots' appearance is exactly the same. So this is what we call the correspondence problem in motion perception. What corresponds to what from frame 2 to frame 1. So this actually leads to what we call the local ambiguity, and then we also call it like a aperture problem. So for example, in this case, I can move and then the object behind the aperture, behind the hole, all you can perceive is within the small spatial region how this object moves, right? So now, and then in this case, you can think about it, it's almost like one neuron and have this limited receptive field. This is what one neuron can see. But what's this local ambiguity come from? So now we have like one edge, the edge in first frame, the edge in the second frame, because all these points on the edge, they have the same appearance. They could go to, and then basically this line, and then could go this way, and probably most of you perceive, or could go this way, because the line could be very long. And I can only see, and then these types of within the limited and the space. So that's indicated by these red arrows. They are all reasonable answers, and then to the movement. But what you perceive, and typically, is the shortest one. So this is the kind of what you perceive here, is that they go up and down and 45 degrees, and then you have some kind of preference and then to choose, and then among and all these possible answers here. So this actually later, and I will talk about related to one of the preference. But now the other things is like you can see here, you have this local ambiguity. If I only can see the object movement and from this one hole and or from this one receptive field of the neuron, but actually what the object is moving is on the left and the right horizontally. How could a visual system solve that? So the biological system, and then now surprising, I add another neuron. When I add another neuron, and then I can see it. Now, but the question is like, this will be an integration problem here. Now, for each of these neurons, and you perceive and some motion direction, how you are going to integrate the information together, then you can tell me and the object behind and these apertures move and the left to right, back and forth. So in vision science, and then there has been a lot of kind of theories, and then try to explain and then these types of the behavior. So the stimulus we have been using is you could have like two different oriented lines, and then you can have the different integration mechanisms. I'm not going to get into the detail. Is that one mechanism is that we really look into and the orientation as the lines of the orientation as a constraint for the movement. We combine them together and we looking into this intersection with the constraints, and we should predict and then this object, actually this plot, will move and horizontally. Or I can get under the movement, and for each of these lines, I can do a vector averaging. Then I predict that, and then this whole thing, people's perception will be moved like a downward and 45 degrees. Or I can do a feature under the tracking. So that's kind of usually used in computer vision. Now, and this kind of intersect point, it's interesting because it's easier to to solve the correspondence problem. I just track these features. And then that makes a difference in the prediction. So in the past, it's like, but the one thing from experimental data is that it's very dissatisfying, because we notice that even for this very, very simple experiment, depends on the shape of this rhombus. If you imagine you have put a few holes here, and then you ask people to perceive the motion direction, depends upon the shape of the rhombus, basically the orientation of these lines, depends upon the contrast of this rhombus. And then people's and the judgments keep changing. In some situations, and then satisfied and kind of consistent with this theory. In some situations, consistent with other theory, and so on. So we don't have a very kind of coherent and parsimonious theory to explain how people integrate the motion information. So if we just adopt the Bayesian ways, and then now we can look at the problem from the computational perspective. What we have here is a set of the image frames, and what we want to infer is the velocity of this object. We can decompose it into the likelihood and the prior here. So the likelihood, and we add constraints. So in this model, the constraints can be added is that within a very short and spatial temporal windows, intensity of the object or the image will not change, and the velocity will not change. So here, the emphasis is in this very small and the spatial and the temporal regions. So we can use this constraint, you can think about it, provide your local contrast, local context constraint and to this likelihood computation. And we add how this kind of data can be generated. So if we add these types of constraints here, so this is a little bit complicated graph, but I just gave you the essence here. So now this is the stimulus, and then, this is another stimulus and has a much low contrast here. You can imagine, and then you have a different apertures at the different locations. People can see and the movement of this edge in the aperture A, and the movement of this corner in aperture B, and the movement of this edge in aperture C. And now this one has a high contrast, this one has a low contrast. If you implement this likelihood, and then you look at what velocity give you the highest chance and then to produce and this observed image frames, what you notice that maybe the easiest one to look at the B is that if you look at the corner movement, and then if you have high contrast, the likelihood to tell you with high certainty tell you and the movement and basically moving to the right. But then when you have the low contrast, and then you can see this uncertainty increase here. And then this is from the same computation to become and then sensitive to the contrast of the image. Now for the prior, we also can introduce the prior. The first one is that you favor slow motions. The basic idea is that if you look at the world and then currently and then in this room, most objects, they don't move. And then they also have the natural statistics and to back it up. And from computer vision literature, if you measure the natural statistics of the movement, you get this very nice and then these distributions. So you centered at 0 for both the horizontal and the vertical velocity, and then you have the heavy tail here. So if you introduce and then these types of the prior distribution in terms of velocity, you can combine them together. Then you will notice that if we change the contrast of this rhombus, and then you predicted the velocity direction in your perception will change. So that's actually consistent with the human and the judgment and so on. So you can just like do these types of the experiments. You can change the contrast. You can change the shape. And then so in this is one example from the study. And then open circles and indicate the human judgment, their perceived movement direction, and the lines and indicate the model judgment. And you can see and it's matched and very well. So now if we want to see and then human motion system is actually doing these types of computation, so the important things is that you don't see this consistency or convergence and from one experiment, you are going to see it and from many different experiments. So this is actually in the literature, you can manipulate the shapes, the contrast, and the different properties. You can see the same model actually can account for human judgment and pretty well. And so this can give you the basic model, but then you can also easily expand on top of that. So for example, you can, one of the aspects you can expand the prior knowledge. So here, and I just show you a quick illustration, I think it's fun, is that now if you perceive, if you look at the movement, what you kind of have the different perception about the movement of this ellipse. On the left, it feels that the ellipse is doing the rigid movement back and forth. But on the right, and basically you feel like this ellipse is doing the deformation and also move and slower. But if I tell you all change the ellipse, they're actually doing exactly the same movement. But by adding and then the different, the movement of these 4 points, it completely changes your percept. If I cover the points, and for the first one, I cover the point for the second one, you can see the ellipse is the same. But then your percept is dramatically different here. And then so this is kind of like your mind and then doing the trick. And then what trick is doing, because the computation and you used to do to analyze the videos, and then they do the same computation and to this illustration, and then that can change your percept. So the change of the percept, it really comes from the movement of these 4 dots. Why? And a part of the reason it can explain this illusion is to introduce more prior knowledge here. Not only we favor the slow motion, we actually favor the smooth motion because the object features tend to move together here. So you can, this actually also have the support from natural statistics by measuring on the videos and so on. So what you can do is that you can increase, you can change the distribution for the prior distribution, not to introduce the slowness by adding more higher orders. You can introduce the smoothness motion. So here is just like illustration here. So first order smoothness, you prefer the 2 dots and move together, share the same velocity. And the second order, they share the similar acceleration and so on. So we can introduce and then this prior distribution and from smoothness and then to account for human motion perception. So it turned out this is the more powerful. And then across 16 different studies, across a variety of the like a stimulus type, and then this model can account for human performance pretty well. So what I'm trying to show today is that if you could have a strong version, you could say, okay, and then this cognition can be described by these rational types of models if you use the right prior and the likelihood. But I think the $1 million question is that what are the right prior and the likelihood and people use? But at least in some cases, at least in these 2 examples I'm showing you here, we have a ways and then really and then to uncover and what's the likelihood, what's priors people can use, And this mathematical foundation provides us a very good tool to study human intelligence. Thanks.